Right, so we are going to talk today about the second part of the coursework, and the idea is to clarify minor details, and the most important aspect is to specify exactly what you need to complete and put in your report eventually. So it's our coursework part 2. The first part was discussed in the previous lecture. So the aims for this part of the course, or for this talk, basically, right? It's specifications. Will be the next slide where we will find what exactly we want to complete and include in our report. And please note that in this school, 100% mark is quite difficult to achieve, and the merit level is 60%. Therefore, well, if some of the specifications are not implemented, then it's also fine. Then there will be a few diagrams with the control system architecture and the two experiments, and these two experiments are very similar to each other, just the control system is connected to different network devices, different Raspberry Pis. So it's either both the input and the output of the control system are connected to the same Pi or to different Pis with communication over the internet. So the whole idea is to introduce in the second experiment this complexity of using the network, and the network will add to the lag or latency in the system, and it potentially will render our system unstable, or at least less stable compared to the experiment number 1, where the lag is shorter. It will be still some lag because nothing is infinitely fast. Just when everything works in the same computer, then the lag is minimum. Then this is the point. I would like you to measure the step response of the system. It's not sufficient to say that in the first experiment the system is more stable than in the second experiment. What does it mean, more stable, right? So stability can be viewed in diagrams. You just apply a Heaviside step function to the input of the system, and then the system starts oscillating and settles down on some particular response. And the response now, in our case, will be rotational speed of the motor, and the transition from 0 speed to a fixed speed, in our case, will be 2 rotations per second. This transition can be plotted, and if there is plenty of over-regulation and it's oscillatory behavior which is observed, then it is kind of unstable system, and if this gradually approaches the required speed and kind of stays on that, it will be stable behavior. So it is possible to measure things rather than just to chat about this. So I suggest to use the measurement. And there will be a slide later on about how to do that. It's not that difficult. Basically, it's about dumping the output of the sensor into a file and then analyzing the file, possibly plotting it by using some tools. And then there will be plenty of slides. Well, it's not the aim of the coursework, but rather the aim of the of this lecture to give you tips on C programming, which libraries to use, and there are examples of code, and many of those can be just cut and paste into your designs. It should be helpful. So first things first, so the specifications for the coursework. There are 3 fat red bullet points. That's what we want to do. First of all, we implement a closed loop control system for an electrical motor, right? And it will be run on different devices, and where it is run is the third point. The second bullet point here is that the system consists of components, and the components of the system need to be implemented somehow. And the components are the encoder program, the controller program, right? And the third one is kind of a minor target, which is means for step response capture. Why do you want this encoder and controller programs? Because the first one reads the data from the interrupt and from an additional wire coming from the sensor, which measures the speed, the rotational speed of the motor. And it has to be those pulses which come from the sensor, they need to be processed by our computer. So it will be a program encoder. And when designing this encoder, we need to choose the appropriate sample rate, format, method of frequency measurement, and so on. When I'm saying to choose, I can recommend some particular values, and this is known to work, right? However, when you are choosing, you are adding your own, not just opinion, but argument towards the choice of some particular values. And you know that the rotational speed can be measured by two methods. The first one is to measure the number of rotations per a fixed interval of time. So how many pulses come from the sensor within a fixed period of time. And the other is to measure period. So you have this period which is one interrupt and the other interrupt. So between the interrupts you have this time interval, the period. And within this period you can fit multiple number of counts of a timer. So there is a software timer in the system. You can say that now I start the timer, now I stop the timer, and it gives me the value, measured value between the start and stop. So what is better? Well, it's up to you to decide. The encoder, well, sample rate is also kind of up to you to choose, because you can have a very, very high sample rate, for example, and if you try to measure the frequency within a very short sampling timing interval, then there will be not many pulses coming from the encoder sensor, and therefore the measurement will be not accurate at all. Right? So on the other hand, you can take this sample rate like half an hour, and you will accumulate plenty of samples and will be very accurate measurements, but the lag will be huge, then it will be probably not useful in controlling the motor. So somewhere in between there should be the optimal value for our design. I'm using 20 milliseconds in my sample examples. Well, I thought that was reasonable. The format. What I mean by the format, when you output the samples, you can output as floating point numbers, and Raspberry Pi is the device which we are using. They have a coprocessor, so it's easy for them to compute values in floating point. However, another option is to use integers, because essentially what we do, we count the pulses within a measured period of time, right? So the number of pulses, it's an integer, and then there will be no conversion to floating point. Perhaps it will be a faster version. In the floating point, you probably want to output the data directly in units of hertz. In integer, well, our rotational speed is quite low, so 2 hertz, and small deviation will take us down to 1 hertz, maybe less than that, and the rounding error then will be huge. So if the format is integer, then probably the values will be hertz, where 1 hertz is 1000, so it will be millihertz, right? So in millihertz, it will be a rather kind of nice representation of numbers, in the sense that the rounding error of integers will be not large, so significantly lower compared to the error which happens due to the choice of our sampling rate. Okay, method of frequency measurement, as I said, that could be either to measure frequency or the period, and we have discussed those both methods before, and you need to choose which one is better. In my reference design, I used frequency measurement, so I had this interval of time, 20 milliseconds, and within 20 milliseconds, I measured the number of pulses coming from the sensor. Well, this is the recommendation. It is put into the specs because it's just easier like this and easier to mark such a work, and most likely it will result in shorter implementation time. I suggest to provide the output of the encoder program at the standard output stream of the program. Right? Why? Because you can observe it on the screen straight away then when testing the program. And then when this program is used together with the controller program, then we can forward the stream from one program into the other through a secure shell. And then these two programs potentially can sit in different computers, and we will have our experiment with the distributed system. All right. Now the controller program. It's another component, software component. I suggest to have a target rotational speed 2 Hertz. It does need to be 2 Hertz, plus minus 10 Hertz. It's the range of useful speeds for this motor. Well, actually, the motor can do more than that, but above 10 Hertz, the encoder will start failing because the interrupts will be so closely spaced that the lag in the interrupt system will start showing up as lost samples. So 2 Hertz is well within the range of plus minus 10. So there will be no problems with performance of the interrupt system. So I'm suggesting to have this rotational speed. Again, this rotational speed is quite convenient to observe through the video camera when you're looking at the motor. So by naked eye, you can estimate roughly, of course, the rotational speed. Well, this is a fixed value, by the way, here, right? So in your program, it will be probably represented, at least at first, as a constant. Please keep this in mind when reading the last bullet point in the specs, and then we'll say that probably at some point we will need, actually this one together with this when we will need to find the step response function, right? Step response means that instead of the input, which is fixed 2 Hertz at the beginning, right, we'll be applying 0 Hertz or no movement at all, and then 2 Hertz, and then 0, then 2 Hertz, 0, and 2 Hertz, and then we'll see how the motor accelerates and decelerates. Right, and we'll be looking at the overregulation there. So at first, this will be a constant in your controller program. And then we will replace the constant with a variable. And for the sake of the next bullet point, you will represent it as a variable, and you will be changing it in order to perform the next step. Right. Okay, the next bullet point here is the next component. It's means for step response capture. Right? Means for step response capture. That's what I said. We may want to modify our controller program so the input speed was not constant but variable, and variable in some particular sense. So sometimes it is nothing, 0, and sometimes it is fixed speed 2 Hertz. And then we will be looking at the transition, how well the system transitions from no rotation to some particular rotational speed, and whether there will be oscillations in the speed or not. All right. Once these means for step response capture have been implemented, so this involves, as I said, this part plus recording of the output, and the recording will be just dumping the data from the sensor, from the encoder, into a file. So we will eventually plot motor speed versus time as a response to Heaviside step function. Finally, we would like to test the stability of the system on the same device and between two devices on the same or different lines. So this is the study of impact of Internet of Things type integration. So when Internet links are included into the control loop, right, on the stability of the system. So of course there will be an impact because Internet introduces lag, which is latency, and latency in the control loop makes the system prone to oscillation. Usually, in order to avoid this, one has to reduce the gain, loop gain in the control system, and this is achieved by reducing the coefficients. You remember we are using PID controllers, so it will be proportional integral differential coefficients. There will be probably reducing them in order to make the system operate once connected to LAN. The same or different LANs. So we have plenty of LANs in our network setup. And every time when packets are traveling between different LANs, they have to be passed from the network interface card into the processor of the gateway device, right? And the processor will do the magic. It will unpack it and it will pack it back. So it unpacks the Ethernet packet, looks at the IP header, right, the IP address, and packs it back into a different Ethernet packet and sends it over a different LAN. So these actions of the microprocessor are usually slower compared to the action of just the Ethernet card, and you will see the impact of that on latency, and the latency will have its impact on stability of the system. Right, so this is what we want to implement eventually. Although there are many bullet points, but I think they are mostly a clarification of each other, because eventually we want to have a control system working, right? And working when the system includes in the loop a segment of the network. It could be either a single LAN or several segments, actually several LANs. So basically, such a long text is only kind of provided only to specify the components and clarify the components of the system. No, you have seen this picture already when we discussed the architecture of the control system for the experiment. This is a control loop. This is the input. Right? In our case, it is 2 Hertz. Right? This is the output, which is the rotation of the shaft. So the parameter here, the measured parameter here is the rotational frequency of the shaft. Right? And it's measured by this device, which is the encoder. It gives the numbers, and the numbers come back. They're subtracted from the demand of the kind of the digital input. And the difference is the error, and the error goes through the PID controller, which we have discussed before. And the appropriate kind of value is applied again to the motor, either to accelerate it further or to slow it down, depending upon the polarity of the error. And again, if there is a small error, then there is a gain here, and this gain will increase the value, and as a result, the action will happen, and even a small deviation on this side will result in a significant kind of modification of the speed, and then the speed will hopefully come to the desired value. I'm saying hopefully because you have seen from modeling that it may or may not happen. Sometimes systems become unstable. Latency is here and pretty much everywhere. So here the latency is the latency of what? Of the program, first of all, right? Programs are not very fast, but still they're quite fast, as Raspberry Pi runs at 1.4 gigahertz. It's fast. The latency is here when we are interfacing our program to the driver board of the motor, and there is RS-232 interface, this one, right? And RS-232 interface is not the fastest on Earth because its speed is 19.2 kilobaud, and for each symbol it uses 10 bits. Out of those baud it's bit per second. And if you add things together for several bytes which are sending across, then there will be a significant latency expressed in milliseconds. It was calculated in the previous lecture, and we can have a look at this. There, the source of latency is on this side. What is the source? When we are sending pulses here, there is a counter here which measures the numbers of pulses coming from the encoder within a measured interval of time. If it is 20 milliseconds, then 20 milliseconds accumulation time gives us around about half of that, 10 milliseconds of lag. So 10 milliseconds of lag is here, and also the program itself gives us a fraction of a millisecond latency. So the latency accumulates, you see, accumulates. Then there will be a latency here. So a pipeline within the same host is reasonably fast. It's a fraction of a millisecond, but when they are sending the data between the devices on the same or different LANs, there will be significant latency. If you ping one device from the other, you see those lag values explicitly. So there will be some latency here. So altogether, those latencies will accumulate and will contribute to stability or lack of stability of the system. This is what I said here. The input will be 2 Hertz. It will be constant at first, right? But when we want to do this, means for step response capture, right? We will need to generate this input, which will be first 0, then after a second or 2 or 3 or 5, it becomes number 2 Hertz, right? And then becomes 0 again, and it becomes 2. So it will be alternating between 0 and 2 with sufficient time separation. What do I mean by sufficient? Sufficient needs to be so long as needed in order to finish the observation of the oscillatory process, right? So it depends upon how well the system is designed, right? So in our case, I think that something like 5 seconds will be more than enough. So if the system doesn't settle down on some particular rotational speed within a second or 2 or 3 or 4, it will be a rubbish system. So 5 seconds will be probably a safe value for this period. Although many of you will achieve the time constant somewhere within a second or a fraction of a second, then we potentially can do this alteration faster. But for the sake of the experiment, probably it makes sense to start with something like 5 seconds. It's my kind of thought from the based on the initial approximation. Now, the experiments. You remember I mentioned here that there will be test stability of the same device between 2 devices on the same or different LANs. So that's the picture from our previous lecture on design of the LANs. So we have multiple LANs which are shown as different colors, right? Those machines here, these are Raspberry Pis which are programming. And at first we connect the control system This is driver board, and that's the output of the encoder. First, we connect to the same pi, right? Why is it this pi rather than any other pi? Because I just decided to do that like this, because this pi is easier to access, right? This pi, even if it is in the mastering mode, it still automatically is attached to this network, so it's guaranteed to work. So minimum effort on any sort of networking issues here. And this is the most favorable case because no extra latency is added into the control loop due to the networking. So once everything is done here and the system works and you have a very nice step response function, you're happy with this, then you can proceed to the next stage of the experiment. At this stage, our technicians will rewire our system. They will disconnect the encoder from this machine and connect it to the other machine, right? And then you will be using secure shell, a chain of secure shell connections in order to reach this machine. And as a result of that, there will be a log in the system, and the properties of the system will change, and the step response will be different, worse than before. So you will draw a conclusion, which will be that networks do not help construct control systems, and that the problem can be alleviated perhaps by changing the parameters of the control system, reducing their values. Typically, when you reduce the values of the coefficients in the PID controller, the controller becomes more stable but more sluggish. So that will be the second phase of the experiment. Now, step response measurements, which I mentioned before. So the idea is to modify the controller by replacing the constant input, which is originally 2 Hz, with a variable. So instead of a constant, you'll have a variable. So constant is declared as constant, and then the type, and then the value is constant, right? And this will be just a variable, so the word constant will be removed from the declaration. And a small piece of code is added, which is on time changing the speeds, the value. Sometimes it's 0, sometimes it's 2, and the period will be probably about 5 seconds. That's a sufficient period. Then we need to record the output of the encoder, right? So it's not just change the speed and observe that the motor first stands still, then accelerates, then stops and accelerates. So you probably also want to somehow record this in plot. So how we do this? The output of the encoder is normally connected to the input of the controller through a pipeline, right? So what we want to include something into this pipeline. It will be a new process, and the process is T. It's a program which is a standard utility for Linux systems. So you'll put the T with some parameters and read the manual file for this. Right? How to do it? Type man T, and you will see how to use this T in order to pass one copy of data through, and another copy of the same stream will be created, and potentially it's possible to redirect it into a file of your choice. And then you will log whatever was passing through this pipeline. And after that, you can take this file and plot it somehow. Right, which leads me to this bullet point here. Find a way of plotting the data in this file. And the data will be just number, one number per line, right? And the numbers are either integer or floating point. So I need to find a way of plotting the data in this file. One option is to use MATLAB and or probably a spreadsheet of some sort. Another option is to use the same Raspberry Pi and just use a GNU plot utility. It is a very old and high quality plotting utility, very compact as well. So how you start it, you type GNU plot, then it gives you some sort of a prompt where you can type things and then say plot samples.dat, and samples.dat is where you dumped the data by the command T, right? And this plot samples.dat with lines, Why is it 2 here? Something went wrong when I typed it. Just with lines without 2. So I will modify this slide for a correct kind of command here. Correct will be without 2, but with quotation marks instead of 2. Right. So samples.dat, it's a file with where you have data like one number per line in almost any format, because GNU plot can recognize plenty of formats. In our case, it will be most likely just integers or floating point numbers. GNU notation. Right. The stability issues. So our system, once implemented, it may work or may not work. By not working, I mean it may start accelerating the motor and then sort of decelerating, or just the motor may just run away, so start rotating at very high speed and never return back to the normal speed. So if not stable, adjust the coefficients of the PID controller. Right? Or it can be just a bug in your program. Because typically, when in the course of experiments you see oscillation, normally it's to reduce the gain, which helps. The gain means the amplification within the loop. So it's governed by the coefficients which sit in front of the proportional, integral, and differential components of the controller. So if you reduce those values, then usually the whole system becomes stable. It's potentially possible to find a unique example where it's not the case, but in most cases it happens. So if you reduce the values, then the system becomes stable, stops oscillating. Usually becomes slower as well. By slower, I mean it takes more time, longer time to settle down at the requested speed. Now, we are done with the specs, and I have a significant number of slides following this one and following. It's about programming. Usually programming in C language causes a bit of anxiety because we don't have much experience with this. So I decided to enhance this experience of yours by including these slides, this information. First of all, I'm suggesting to use that many libraries, and this is a quick explanation of what we do, what we use these libraries for. The first one, stdio library, it is the place where the functions printf and fflash are defined, right? Printf, it's for printing something on the screen or standard output, and fflash for flashing the buffer, because printing happens not into the stream itself, but rather into the buffer which is sitting inside the stream, and fflash actually causes this buffer to flash it out. So for example, your encoder will be producing the output data by using printf and flash. The next library, unistd, right? It includes such useful functions as usleep. It's sleeping or delay for a particular number of U units, right? It's microseconds. There's also lseek and read. Read, it's for reading the data from a file. lseek is for positioning the point where we are reading from the file, right? So if you lseek 0, then you will position the reading head at the beginning of the file, and then you can start reading the entire file. Why do we need this? You will see it slightly later when we are processing the interrupt. Then the interrupt is associated with a buffer as well, terminal. And we need to, every time between the interrupts, we need to empty this buffer by reading it. So for this, you need move the position of reading to the beginning of the buffer and perform the read operation, and then we are prepared for the next interrupt. So believe me, it's the case, and it will be described in a couple of slides after that. System is from stdlib. So what is this system? So this is a function. In these brackets, you can put a formal parameter, which is a string, and this string will be executed by means of a shell. So whatever you normally type in the terminal can be put here, script in shell script. And then the operating system will do it for you. So you will see very soon how it is used. Now, poll library is the place where the function poll sits, and the function poll responds to the interrupts. That's what we need to process the interrupts. This function actually stops and waits, and then becomes released as soon as the data arrives. So the interrupt arrives and some response in our program happens. So this is how we sense the interrupts. Open. It's for opening files. So those files which we read or position our reading device within the file. The files need to be opened somehow, right? So it's this library, pcncl. Now, this library pthread, you have seen this already in the previous course. It's for creating new threads and mutexes. Why do we need those? If you remember our lecture from, it was the second last, perhaps, lecture, right? Before that. So it was the lecture about the algorithms for example, encoder, and the encoder is within a measured interval of time. We count interrupts. So one thread forms this measured intervals of time. Right at the beginning of this interval, it resets the count, and then the counter counts 1, 2, 3, 4, 5 as the interrupts hit us, right? And then at the end of this measured time interval, we read this count and produce the output. Right? So the idea is to have two threads, and threads are created by the functions from this library. So we will need the thread mutex unlock, lock, and actually the thread create. And finally, if you need, but you may not or may not need this, right? So it depends upon the method of measurement. So if you measure frequency, then you don't need. If you measure the period of the timer sequence of the interrupt, then you will need this. So it's either use it or not. Is this library time? So it includes timers. You will probably also need it. No, I'm wrong. I'm sorry. I'm wrong. You will need it anyway. So this library contains the function for the measured timed interval for the counter of interrupts. Yes, you will need. Right. Another helpful slide in programming, setting up general purpose input output. You have seen this, almost this, in fact. You have seen those statements like echo 9 goes into some sort of a file, right? It was when we were operating general purpose input output by hand from a shell, right? Here, this script from here to here, from this point to this point, this script, shell script, is encapsulated into the system, open brackets, quotation marks. So it is a string sitting inside the formal parameters for the call to the system function, right? So basically, this is an example of how we can run a shell script from within a program in C. The numbers here, 9 and 10, these are general purpose input-output pins, which we are using in order to access the encoder. And the pin number 9 corresponds to the interrupt, and pin number 10 is the second additional input which is needed to determine the direction of rotation of the shaft. The appropriate diagrams of how to do this, the methodology of measurement, was discussed earlier, so I'm not focusing on this now. How to distinguish who is who, 9 or 10 on the interrupt. So you see 9 is the input, and 9 here, GPIO 9, is programmed to respond to the rising edge. So edge driven, it means it is an interrupt. The pin number 10, you see it's created here, export, right? Now we have this directory. The direction is input, edge is none, so it's not responsive to edge. So basically it will be just a value of that which will be available from the file, and the file will be sys class GPIO 10 slash, instead of edge it will be the word value here. It's mentioned further. Well, you can do the same in a more sophisticated way if you wish. Check first if the appropriate GPIO is already enabled. Look, you see first here I say that the GPIO pin number 9, first just kill it, unexport, right? And then create this interface from scratch like this. So number 9 goes into the file export, and after that the appropriate GPIO 9 directory is created, right? And has the files inside, which are the interfaces to direction, to the edge control, and so on. If this GPIO 9 does not exist in advance, then the first statement, this one, which demands to destroy it, will cause an error and a warning message. It will say that, it will complain to us saying that there is no such interface anyway. So what I mean by the more sophisticated way of doing things, we can first check whether this GPIO 9 directory exists. And if it does exist, then you can do an export. If it doesn't exist, then don't do this business. And as a result of that, you will not have the warning message. It's not important for us, actually. So don't waste time on more sophisticated things. Well, the same mechanism of programming, setting up the GPIO, general purpose input output, can be done with the file access commands of C. So what are those commands? These are open. Open a file. Which file? Every time we are dealing with files. So that's a file, right? This is a file. This is a file. So you can open, close, open, close, open, close files. And once the file is open, you can write something into this, like this, like this, appropriate strings, right? And you write by command write. And then you can read some value from the appropriate files. And you read by command read. And this and these commands, they are functions, and they sit in the libraries which you mentioned before. So it can be one way or the other of doing things. I suggest not to struggle much. This method here is good because it works and because it matches our previous experiments with a shell. Right? It's not the fastest because it has to start something at the system level before actually get the result. But this is done only once at the beginning of the program, and the delay of a fraction of a millisecond to several microseconds will not be noticeable to you in any shape or form. It makes sense to optimize things only when they're in a busy loop and when latency is critical, may cause malfunction at some point. All right, the second tip or hint of how to use interrupt. So this is a piece of code inside your program. Consists of 1, 2, and 3 parts. The first part is the setting up part, so we need to declare a structure of the type poll fd, whatever it means, file descriptor for the poll, and give a name to a new object of this type. Right? The type is declared inside the library, which is poll, and then you will put something into the structure. And how to know what to put there? You have to read the manual. I did this reading for you, so I'm providing an example and it will start working if you go by example. But it makes sense to read this as well. Why is it a structure? Because the designers of this library decided somehow that it's better to pack everything in a structured way into a single object whose internal organization is a structure, because there are more than one value which are needed. So you see this PFD0, its field events has to be programmed like that, and other options will not work. I debugged this, it works. This is to enable events, right? So each of these guys, it's a bit mask, and we have bitwise OR between them, and each bit corresponds to enabling of some particular features inside. Why this poll error is required? Don't ask me why, because it is a very, very long discussion. Read the manual for the poll function. It has something to do with dealing with interrupt-driven terminals. It's inherited from a long, long chain of products. So believe me, that works. So just use this. It's lame. Now, PFD0 is the same object, but the field is FD. That's a very important one because we put there the output of the function open. And the function open, if you type man open, it will give you the manual for this. It says basically that once this function has been executed, it returns the file descriptor or a number. A number corresponds to the number of the open file. And then you can refer to this file by the number. So the file descriptor needs to be provided to the library. Why? Because we need to inform it on which in which file the buffer of the terminal sits, and the terminal, it's the kind of excessively complex concept which is attached to the interrupt. So we cannot access just raw interrupts because it is a high-level operating system. We have to do the next best thing is to use a complex object which is linked to interrupts. So instead of raw interrupts, we are using the terminal and operations on the terminal. So this is the buffer. Once this GPIO9 directory is created after we exported those values, inside this is the file value, and the file is actually not a real file, it is an interface file. It is the image of the buffer associated with this terminal. And we open it in the mode read only and non-block. Right, so we open the file. Right, so this is the stage of preparation. So we need to somehow turn the attention of the poll function and poll library towards some particular interrupt and some particular, let's see this guy, some particular buffer. And after that, we can start using the terminal. How we use the terminal? We need to first make sure that the buffer is empty, right? How to make sure it's empty? You just rewind the reading position to the beginning of the file. It's lseek, right? In this file with the file description, we move the reading position to the position 0. And the command is set this position. So from now on, it's there, it's changed. Then we perform reading from the same file, right? What we read the string. The string is size 1 because there is not much in the string. It's either 0 or 1 in ASCII format. So why is it 0 or 1? Because if you type cat space, then the path to the file value, you will discover that it has either 1 or 0 written in it, and 1 or 0 it's an ASCII code rather than a binary value. And apparently it's not just a character, but a very short string. Called string by its type. So once this is done, the reading of the buffer is finished. After that, the buffer enters the state when it is waiting for the new data, and then this function poll applied to the same buffer. What it does, it causes a delay. Basically, it starts and sits there waiting until new data has arrived. Right? After that, after waiting is finished, it will read basically one character into this buffer, and this number corresponds to the emergency situation. It's 1000 milliseconds. It's a timeout. So if nothing happens, then the function will stop waiting after this timeout. Why is it done? Because if nothing arrives to this buffer, then we may have a deadlock in the system. So everything is prepared here for the programs which don't have multiple threads potentially, and to unblock them. In our case, this number is not essential. So if you put here 1 million, 10 million, just a large number, then it's fine, because we don't really need the time. So this is the key aspect of waiting for an interrupt, the key aspect, right? And then after this, we may want to do this again and again and again and again. So this manual sheet, how it works, you see? After that, I say here that we need to do lseek and read again, so it's the exact copy of that, right? Then poll again, consider a loop. So this construct should be somewhere in the loop. What is this loop? Please refer to the block diagram of the algorithm, which was discussed when we looked at the encode algorithm. The next topic is to read the general purpose input-output pin. So before that, we were waiting for the data to arrive to the terminal, so for the interrupt. Now we are waiting for another, not waiting, but reading a pin. Why do we need it? Because when the interrupt arrives, then we look at the other signal coming from the encoder. And if that signal is 0, then it means that the whole rotation is happening one way. If it is 1, then rotating is the other way. It's clockwise versus counterclockwise. How it works, I had diagrams before, it was discussed before. Please refer to the previous lecture for details. So there is no polling here. Instead of that, we are creating a file descriptor. Why do we need it? Because we are prepared to open a file of some sort, right? So we need a file descriptor of integer type. And this file descriptor at the beginning, it is just an uninitialized integer, right? It will become initialized later. Now we declare a buffer of sufficient length. And this buffer will receive eventually the values coming from this value, right? So basically it will be just one character there, but this character also comes together with the terminator. So it has to be a character and then finish with binary 0. So why is it 4? Actually 2 will probably work as well. Now file descriptor equals to open, right? So open function like before, if it is successful, it returns the value of the file descriptor of the file which is open. And which file we open? This file we open, right? And this file is present in the system. Why is it present? Because it was created ages ago, like this, right? Then goes into here, and after that you see the new directory is created, and in this directory, if you look at this, there will be many files, and one of them will be this one. Okay, it's open in the mode read-only and non-block. You can open it in a different mode as well for writing, for example, but it's important to be able to read it at least. So we never write into this, we need just to read. So it's the appropriate option. Write, read, it will be excessive permission. Also, after that, we need to do else seek to rewind the buffer, set it to the position 0 in the file descriptor 1, and this file descriptor 1 corresponds to the previously opened file. Position 0, add action seek set, so set this position of reading that 0. There are several other commands. If you're interested, those type man lseek, and you will get the full manual for that. And after that, you can start reading. Read from the file defined as the file descriptor is the same as this one. It's the same as this one, right? You are reading the string, and reading just string size 1, a very short one. It will be just one character, and it will be finished with the end of file, the terminator string, the terminator symbol, which is binary 0. All right, and after that you can seek read again, and so on and so on, and every time you will be getting some values there. Does it make sense? So the input happens into the string, and if you want to take an action based on the string, you need to look at what contained in the string at the position string and in brackets 0. It's either ASCII code for 0 1. Note that there are ASCII codes in the string, not binary codes. So I need to compare them to the ASCII symbols. Right, frequency measurement. It's a quick reminder. Before that, we have discussed that it can be frequency measurement or period measurement options, right? Frequency measurement. It's you need to use 2 threads. One of them will be using interrupt as a poll function, right? And the poll function will freeze for a moment the loop, and then it will unfreeze it when the interrupt arrives. Then the loop completes, and in the loop, an increment of a global variable happens, right? And this global variable is used by the other thread as well. Now the other is timer thread. It reads the global variable every 20, in our case, maybe 50 milliseconds will also work, and calculates the frequency of interrupt. How does it do this? So first it sets this counter to 0, which count? Global variable, right? Which is being incremented. Sets it to 0, and then after those 20 or 50 milliseconds, it reads it again and calculates the rotational frequency and produces the output. And then starts the interval again, which means it resets it to 0. So you have seen the algorithms for that. Just make sure that you can remember that this encoder device, it provides 500 interrupts per rotation. So if it is rotating at the speed 2 Hertz, it will be 1000 interrupts, right? So within 1 second will be 2000 interrupts. So the frequency will be 2 kilohertz, right? And 1 kilohertz, right, per second. 1 kilohertz. 1 kilohertz, it's in 20 milliseconds, it will be 20 samples, right? So it will be a reasonable accuracy of 5%. With this interval, it will be even higher accuracy, proportionally high. Another option to measure rotational speed is to measure not frequency but the period. But it has a disadvantage because the output will be formed every time when you have an interrupt. So you cannot use the constant sampling rate, and then our plan is to feed this stream into the other program, which is the controller, and the controller needs to know the sampling period. If it is changing, then there will be complications with that. But it's possible. So it's possible to between the interrupts measure the time intervals. So in a loop, which waits for an interrupt, starts the timer before and reads after the poll function, right? And it has a very low latency, but accuracy is low because the interrupt latency is changing, right? So it's a method which is good when your rotational speed is very, very slow. For example, if our rotational speed is a fraction of a hertz, so it's 5 seconds to complete the whole circle, then it makes sense to switch to this method, because otherwise we are talking about huge otherwise we'll be talking about huge increase in these numbers. That's what we don't want to have. Right. If you have some sort of an error, and the error will be happening due to fluctuation of the interrupt latency within a period, then we will have to somehow post-process the red value. Imagine that you have numbers, rotational frequency or period, right? And they're fluctuating up and down, although the speed is really constant. So in order to remove the noise from these measurements, you need to do some post-processing, some sort of averaging between the neighboring samples is required. So I think that using this method is appropriate for very slow rotational speeds, but it is a complex method. Many complications come from the idea of aperiodic sampling, which is period is changing all the time, right? And the noise potentially present in the system, which requires post-processing. Now, rotation, direction of rotation. If you remember the diagrams from the lecture where I discussed the sensor, the encode itself, it has two outputs, and when the interrupt arrives, the other output shows either 0 or 1. It corresponds to direction. So to implement it in the program, it's quite simple. So at the time of the interrupt, if IRQ5 is 0, if GPIO5 is 1, then rotation is clockwise. Otherwise, it's anti-clockwise. IRQ happens at GPIO9. These 5 and 9 general purpose input outputs are programmed early. Okay, so
is it 10 or 5?
it's a good point. I think it's a typo sneaked in from one very, very old version. It is 9 and 10. It is 9 and 10, and it has to be 10. I will change it in this PDF file. It's sneaked in from a previous version of the setup. Some time ago it was 5. Why it was 5? Because the cable was such. So there was a cable which was wired to the general purpose input output number 5. It's all about choosing the pin on the connector. And now it is a different cable. It is 9 and 10. Sorry about this. As good that you're listening. Thank you. Now the next point is the controller. We have seen the block diagram for the controller, right? It is just a single large loop, and it is operating at the speed of those samples which arrive. So each sample arrives, and then it does the single loop, and then waits for the next sample to arrive. And the samples are words which are read from the standard input, from the keyboard or from the pipeline. Right? Reading them and interpreting those readable textual values is the business of a special command. Let's see, it's shown before, I think. Right? In this system, the encoder defines the sample rate. So those 20 milliseconds, it's the period with which the numbers appear at the standard output of the encoder and arrive to the standard input of the controller. If you want to run them at different sample rates, it's not impossible, but then you will have to put an asynchronous communication mechanism between them of some sort. If you wish, you can try, but it's not necessary. It's about resampling them. And when you do resampling, then there will be errors related to this. So there will be additional noise introduced in the system. It will become less stable. Calculate the error, which is the difference between the reference value and the reading coming from the encoder. Reference value, it's let me scroll back. Reference value, it's not even here. That's the reference value, right? So at first it is just a constant 2 Hertz, right? And then for the sake of the experiment, which one? This one, right? Step response stuff. Right? For this sake, we will modify this. It will become not a constant, but a variable, and will be changing. So 5 seconds is 0, 5 seconds is 1, 5 seconds 0, 5 seconds 1, and we'll observe how the motor accelerates and decelerates. So I need to go back. So it reads the samples. There will be some operation scanf. Scanf reads the text from the input and tries to find in this text the fields. So it will be hunting for either floating point or integer values depending upon your convention, what format you have chosen. Both will work, by the way. So the error between the reference value and the reading is the error, right? So this error is computed with the sampling rate. Then we need to implement our PID controller. In the PID controller, we have integrators, differentiators, and a proportional control. Proportional control means that take the error computed here, multiply by coefficient, and feed it into the output device. Right? How to implement integrators and differentiators by using additional global variables. We have discussed this. Basically, integration means that you keep adding the incoming values to the stored value. It will be integration. Just don't forget that every time you're integrating, that's the integral includes the formula, includes dt, right? So that's small increment in time. So in our case, this increment of time, it's not that small. It is the period of what? The period of sampling. You know the sample rate and the time separation between those samples. It is our dt. So dt comes from here. That's our dt. And in differentiators, it's also dt, just the value divided, the difference divided by dt. Don't forget this. It is in the formulas which are incorporated in our block diagram of the algorithm. Well, our driver board uses the code 737 as 0 input, right? So the valid range of inputs is plus minus 600 to this central value. Actually, it's slightly more than 600. 600 is suitable for all our purposes. The recommended range of speeds for the motor is plus minus 10 Hertz. Above that, we will be choking the interrupt system. Interrupts are not very fast in our system. They have a latency of about 30 microseconds. And at the speed of 10 Hertz, and per rotation we have 500 pulses, will be basically the frequency where the lag in the interrupt system will start dominating the system. At a speed slightly higher than that, it will eventually fail, becomes first very inaccurate and then starts failing. Our speed for our implementation is 2 Hertz, is well within this range. So there should be no problem. But as the system potentially may overregulate, so it will go from 0 to 2 Hertz, but as a transition, a peak may happen, which is 5 Hertz, or 10 Hertz, or 20 Hertz. So if it is 5, it's fine. 10 is fine. If it is 20, then expect an abnormal behavior. So it may register 20 Hertz as if it was some other number, which is not good. And you will see that this will result in a significant error in operation. So the system may just start accelerating because it will decide that the speed is insufficient, although it is exceedingly high. Right, so this is the last hint, because we covered the whole set of components, software components you should design, and the whole set of tips which I wanted to give you. Everything else is just straightforward programming, and many aspects of that programming are covered in the previous module. It's about creating threads. So have a look at those examples as well. They're working examples. You just cut and paste some fragments about how to create a thread, for example. Just rename the names of the variables and it will work. So back to the beginning, we have covered the specifications, literally what to do within this coursework. Then there was the control system architecture interpreted one way and the other way, right? So interpreted in the sense how it is connected to the computers, microcomputers, either to the same computer or to different computers on the network. Right? Apart from the experiment which shows that the system works, right? We want to have the measurement of the step response because this is a way to support the argument in the sense that the system is stable or more stable compared to some other implementation of the same system, right? So what does it mean more stable? In order to support this with a measured kind of value and a firm argument, you need to actually have the structure for measurement of step response. How I suggested to measure this, instead of applying the step function at the time 0 to the system, right? I suggest to alternate between 1 and 0, or 2 and 0, 2 and 0, 2 and 0, right? Alternate sufficiently slowly, and then you will see how the system transitions. And the transition which is of interest for us, it's the transition from the value 0 to the value 1. Why I don't want to have this kind of classical case where at the time 0 we're applying the pulse, because this will complicate the implementation. Then you will need to have an additional input into the system, and you need to press the button and at the time 0 basically, and cause the experiment to be conducted. But the result of that will be the same. You will see the transition, just one of them. So if the system is stable and it has time to settle down between those periods of experiments, that's why I suggest to have 5 seconds separation between going from 0 to 1, from 1 to 0. A sufficiently long separation, then it will be just a series of automatically constructed, generated experiments with the step response. And then I spent plenty of time on tips regarding C programming, and this actually finalizes my talk. Now, please give me your questions.
Sorry, I'm a bit confused. Why the frequency is set to 2 Hz? And another question is PID used for keep frequency stable?
Okay, it's quite simple. First of all, there is nothing confusing in the frequency 2. We can use frequency 1. I decided to use frequency 2 this time. What's the difference? In your case, 2 or 1 or 3, whatever specification is in terms of kind of experiment on step response, it's still 1, because in the step response experiments, we are talking about normalized values, right? So everything is normalized in terms of time and in terms of the magnitude. So the input step from 0 to 1 should be normalized. It's a normalized representation of our physical experiment where we transition from analog 0 to analog 2 Hertz. Right, so it was the first answer. What was the second question?
I'm sorry, another question is PID used for keep frequency stable?
Well, PID, yes. So it was already shown in my simulation results. You remember I used Maxima tool and presented plenty of kind of simulation. There were partly analytical, partly mathematical simulation models. And then I tried proportional control, proportional plus integral plus differential. So It can be P, PI, or PID controllers, right? And they all work, but work slightly differently, and PID is the best out of them, right? Yes, the purpose of the PID controller, and any controller, in fact, is to keep the error small. And
Okay,
at the
thank
same
you.
time, to keep the output roughly the same as the input with a minimum error. Without an integrator, it's quite difficult to have the output exactly matching the input. Why? Because an integral is it's a very interesting block which has infinitely high gain at zero frequencies, right? So it's so-called it acts on so-called static errors. It eliminates a static error. So integrals are definitely essential here. Differential control is added. The aspect of differential control is added in order to move the phase, adjust the phase of the system, and make it more stable. And by doing that, you can allow for high gain in the loop and quicker response. But this is the parts of the control system theory which we are not covering. You have seen my simulations and general reasoning on this subject. If you want, you can read thick books about this. In our case, it's important to achieve at least some functionality from the system. So if it is reasonably stable and you see that the output is roughly the same as the input, then you should be happy with this. And just keep in mind that there is a huge chunk of theory attached to this. Usually it is a separate module. And for linear control, it should be a separate module. And then there are different methods of nonlinear, adaptive control, and so on. It's not covered in our module on Internet of Things and Embedded Systems.